Saturday, Sunday, and don't worry, I'll keep record of it, like of the questions, like in a document like this, and send it out to you guys. But hopefully that'll help you do all the homework that's missing. So yeah, tomorrow I'll have it at 9, and then we can decide from there, like when to have the other times. Okay. All right, and I'll send an email reminder about it too. So, all right. So before I guess we get started, do you have any questions for me? Right. So. All right, so last time we were talking about how we can represent a matrix using a linear transformation using a matrix, right? And we talked about all you had to do was evaluate each matrix at the standard basis, right? And once you do that, you just form the matrix using the columns of whatever's the output. Then I talked about, well, what happens if your matrix isn't in your I guess your good old Rn vector space, right? Well, we have to use a change of basis, and today's basically what I'm going to show you what change of basis is. So I already kind of mentioned what it was here. Which I'll basically just put over here again. So a change of basis is like you just take a two basis B, and let's say you wanted to represent a vector W in that basis. Well, all you have to do is solve this equation for your C's, and I will illustrate that now using an example. So 6.3. So I guess so. Let's see. Okay, so maybe find one that isn't so easy. So find the coordinates of, let's say, why not? X equals 2, 3 relative to the basis B equals 1, 0 and 1, 2. Okay, so all you have to do is do this. Well, just write 2, 3. So this is my X, and I want to represent this as C1, and here's my basis right here. So this is so this is V1 and V2. This is V1 and V2. So basically at this point, all you're going to do is just solve for your C's. You do that by using an augmented matrix. 2, 3. You REF this. Okay, so I guess what we can do is scale that one by and subtract by that. So it'll be 1, 0, 0, 1. This would be 3 halves, and then you get 2 minus 3 halves, which is 4 over 2, which is 1/2. All right. So what does this mean? That means that my C1 is 1/2 and my C2 is 3/2. So the coordinates of x with respect to, here, let me shrink this. With respect to, so x respect to b is just going to be, well, again, just take 2, 3. It's just going to be those components. It's going to be 1/2, 3/2. Okay, so that's how you find a coordinate change. So now this vector has coordinates 1/2 and 3/2, and the other bases. So I guess how that looks like in a picture is basically like this. So I say this is your xy plane, and let's draw the vector 1, 0. Sorry, 1, 0. This is 1, 0, and this is 2. So and this is 1, 2. If you were to look at this as a coordinate, as now like a coordinate space, and you were to plot, uh, I guess the vector, this one right here, uh, 2, 3, and this new coordinate plane, if you were like actually just like draw this like here, that vector is going to have coordinates 1/2, 3. So somewhere around there, it'll be like 1/2, 3/2, and there's new coordinates in these new coordinates basically. So I mean that's all that really means. Okay. So let's talk about something else now. Let's talk about transition matrices now. So now let's find the matrix that actually gives us. So instead of us doing this all the time, let's talk about the matrix that gives us the coordinate change. So now we find coordinate or the transition matrix. From uh, from coordinates b to b prime. Okay. Okay. So what does this mean? Well, so right here for this one, the coordinates, the transition matrix was this guy right here. So if I took this matrix and multiplied by a vector and the standard basis coordinates, it gave me the vector and the b basis. So basically, what this P transition matrix is, so this matrix gives a takes a vector. I guess I'm gonna say and the b basis and spits out a vector in the b prime basis. In other words, if you do b and you multiply a vector x and the b basis, it will give me a vector in the b prime basis. Basically, so what's going to end up happening here. Okay, let's see. So how do you, I guess, find this? Well, there's a couple of theorems that we can use, and I'm gonna, I guess, discuss those theorems right now. Or I guess this is a lemma, or so hold on, give me a second. So yeah, so theorem. Well, what theorem would this be? Three. So let B be the basis with V1 to Vn, and B prime be the basis U1 to Un. So how do you find this P? So then, so if we have that V1 is equal to C1 U1 plus all the way to Cn Bn, and you continue this for each one. Then the C's that make this, I guess you can say this would be C11, I guess you say C1n, and this would be n and n. So the coefficients here are what's going to make the transition matrix. And there should be a U, not a, it could be. Then I can say P is equal to C11 all the way to C and 1, C1n is the transition matrix. From B to B prime, okay? Okay, so let's see. So let's see pretty quick. Okay, so let's do an example really quick on that, or I guess rather, that's not, because you can see. So what? There's one limitation to this theorem, I guess you can say. Well, you can see the limitation to this theorem is that I'm gonna have to solve a bunch of equations, right? So I'm gonna get like, if I have three bases, right, in each one. So if I have B prime with three basis elements and B with three basis elements, I'm gonna have to have three augmented matrices, and then I'm gonna have to RRF this, right? Which does nobody any good. So there's a simpler way. So this has limitations in that it will take a while to compute, right? Well, now there's another one that we can now state. So theorem 6.3.4, which says this. So let, I guess, B be B1 to Bn, and B prime be U1 to Un, be two bases, I guess, in Rn. Then P inverse can be found as follows. Or B inverse P that goes, I guess, from B to B prime can be found as, so you put the vectors in B prime in a matrix, and then the vectors in B in an augmented matrix, RREF this, and the result should give you the identity here, and then the one that's here is the P inverse, a transition matrix from B to B prime. So let's use this in practice now, because now you can see that this is just done in one augmented matrix as opposed to like 5 if you were to have 5 basis elements. Okay, so example, find the transition matrix from B to B prime in R2, where B is going to equal to -3, 2, 4, -2, and B prime is going to equal to -1, 2, 2, -2. All right, so solution, you just use this, the last theorem I stated. So you're going to put this in augmented form, so -3, 4, sorry. So it has to be from, yeah, so you have to put the B prime on first. RREF this, and you get 1, 0, 1, 0, 0, 1, -1, -2, 2, and 3. So this guy right here is your P inverse, and that one goes from B to B prime, right? So what does that mean? That means if I multiply a vector in the B basis, it would give me a vector in the B prime basis. So that's what this would be doing. So for example, just a quick note, just a quick warning. So if I wanted to, for example, see what the vector 2, 1 was, you can't. So if I wanted to find 2, 1 in the B prime basis, I can't just immediately multiply P inverse on this. Does anybody know why I can't just multiply P inverse on this? If I just choose this from Rn or R2. So is this vector right here in the B basis? Is the coordinates there in the B basis? No, this is just in the standard basis, right? So to find this one in the B basis, I would have to first do this C1 -3 to blah blah, and then solve for your C1, C2, and then that new vector is in your B basis, and then you can multiply P inverse on it. Okay, so that doesn't mean I can just take the vector and then just multiply it and give me it. It doesn't work like that. You could, however, find the transition matrix from the standard basis. So basically, well, I mean, that's easy. I mean, you can just, I guess, let's see. Well, I guess it wouldn't be that easy. You could find the transition matrix from the standard basis to B, and then so for example, if I wanted to go from Well, you'll see right now, but like, so warning, don't multiply a vector in Rn to P inverse, since those vectors are not in the are not in the coordinates of B, right? So what you could do is do this instead. So let's say this is from B to B prime, right? Where is it? Yeah, so this would be from B to B prime, and this is my P inverse, right? Um, what I could do is find another transition matrix, say A, that takes me from the standard basis. So let's just call the standard basis, I don't know, E1, E2, there to there, and then to get to from the standard basis to B prime, all I would have to do is do A times P inverse. This new matrix. So you see how if I want to get to here, I would have to travel along this path first. So I could do this, and if I just multiply this matrix with that matrix, it should just give me the transition matrix from the standard basis to B prime, and you can just do it this way as well. And we'll do more examples on it because I know there's a lot of homework problems that ask about this kind of thing. So there's some that ask about it. So we'll do it in those sessions for sure. The book doesn't even mention this, so I mean, it's kind of weird. Okay. All right. So now let us do the representation of coordinates in a different vector space other than Rn. Okay. So now we do coordinates in general vector spaces. For example, find the coordinates of the polynomial p of x equals 4 minus 3x squared plus 3x relative to the basis 1x x squared and x cubed. Okay, so how would you do this? Well, it's the same way. Remember, the definition wasn't just constrained to Rn, vector spaces in Rn. It works in general. So I would literally just have to find, okay, so applying the definition. And I guess if you were wondering what definition I'm even referring to, I'm talking about this one right here. This one. So basically, I want to write the vector w as a linear combination of the vectors in the basis, and I want to find the c's, right? And it's still the same thing, same process. So here, what is my vector though? My vector is p, right? P of x. So my vector here can be 4 minus 3x squared plus 3x, okay? And I want to write this as a linear combination. So I guess you can think of this part right here as w, as c1, so c1 times the vector v1, which in this case is 1, plus c2, let's say v2. So what's my other one? It's going to be C2 x plus C3 x squared plus what's it? Oh yeah, C4 x cubed, right? So this is like my plus C2 V3 and so on and so forth, right? So now, okay, so from here, what should C1, C2, C3, C4 be? What is C1? You should like be able to like stare at it and tell me. Yeah, 4. What is C2? 3. C3? -3, and then C4? 0. Yes. So here, the coordinates of P of X with respect to B is going to be, so C1 would be 4, C2 we said 3, -3, and 0. Okay. Okay, well, that's nice to know, but so what is this telling me? Well, it tells me that the coordinates of this thing with respect to that basis B is going to be 4, 3, -2, 0 in that vector space. So we're actually transitioning to Rn again. However, the behavior, so remember how I told you guys every finite dimensional vector space is isomorphic to a copy of Rn? Well, the behavior, so even though this does not look at all like a polynomial, which obviously it doesn't, it's just a vector with components, it's going to behave exactly like the vector space P of X. So if I find a transition matrix, I multiply any polynomial with those coefficients, it should give me the polynomial in those coordinates. So you'll see here in a second what I mean by that. Let's see. Oh yeah, that's right. Sorry, hold on, give me a second. Yes. So we still have 3 minutes, so this is the next thing I want to do. So find, so example, I guess continuing from the example, 6.3.5, find the transition matrix P from I guess for sorry, give me a second. The basis B. Or I guess in this case it would be B to B. B to B. So all you would have to do is do this. We can use this theorem right here, this one. So we're just going to evaluate everything. So we're going to basically set up these equations right here. Okay. And since we have 1x, x squared, and x cubed, we're going to have 4 equations. But since we don't have to set up a matrix, it's going to be pretty fast. So again, what is B? B is the basis 1x, x squared, and x cubed, right? So you're going to have 1 is equal to C1, 1 plus C2, x plus C3, x squared plus C4, x cubed. And then you have x is equal to the same thing, x squared is equal to the same thing, and x cubed is equal to the same thing. So let me just make copies of this. I guess you should 1, 2, 1, 1, 1, 1, 1, 1, 1. Let's do something like this. So just okay. So for the first one, what is going to be my C11, C21, so on and so forth? I mean, it should be pretty clear for me, right? So C11 would be what? 1, and then all the rest are 0. Perfect. So I'm going to make my matrix. So it's going to be 1, 0, 0, 0. What about the second row? Oops. Well, I guess if you just ignore these, because it should be 2, 2 here, 2, 3, 2, 3, 3. But the second row it's going to follow some, so it's going to be 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, right? So the transition matrix from B to B is just the identity. Now, how do you use this to actually find it? Well, if you have a I guess a third degree polynomial, ax cubed plus bx squared plus cx plus d. If you multiply the coefficients a, b, c, and d, this would just give me back a, b, c, and d. So obviously, that polynomial has coordinates a, b, c, and d in its own basis. So that's why this is the transition matrix. It's just the identity. So you represent the coefficients as a vector, and whatever comes out here would be the new coordinates. So if this came out to be, I don't know, like negative a, negative 2b, 3c, 5c, then your new coordinates would be exactly that for your new polynomial. Anyway, so this is just a sneak peek to what we're going to discuss right now. So that's enough about transition matrices. Let's go back to what we were talking about, which was representing linear transformations as a matrix, right? So now, if you go to a vector space that isn't Rn, you're gonna have to use exactly this change of basis stuff that we just talked about. So now we're gonna talk about non-standard basis for general matrix representation. For linear transformations. Okay, so or well, I guess the same results. 6 point. I think that was let V and W be finite dimensional. Basis with base sorry, I wrote in reverse. With basis B and B prime respectively. Okay, So they both have their own basis. If T is a linear transformation from, say, V to W, and such that, I guess, such that if your value is here, let me let's say B is equal to V1 to Vn. So now we have this basis. Now, if you evaluate T at each of these basis elements, so remember, that's how we did it in the standard basis. Now, take the matrix, take the coordinate change, or find the coordinates with respect to B prime now. And let's say this is just A11 all the way to AM1. And you do this for each one, right? You do this for each of those V's. T of V, oops, B, A1N. Then the matrix representation of T is what? Well, this matrix, A11 all the way to A1N, all the way to AN1, all the way to AN. So now this is what's going to represent the matrix of a general, on a general vector space. So let's finish up basically with two examples. Okay, so let's see. Yeah, so we're gonna use. So remember the linear transformation for derivatives. So we're gonna actually find the matrix representation of that. And you're gonna see how the matrix actually takes the derivative of the polynomial by just multiplying it on it. So here, example 6.3 points. I don't know, what is it? 6. Find the matrix representation of, let's say, the linear transformation from P2 to P1. So the space of polynomials of most degree 2 to P1. So remember this, what does this do? It does this. You just take a polynomial P of X of degree 2 and it spits out the derivative of it. Okay, that's all it does. So with the basis B is equal to 1x squared and B prime is equal to 1x. So this one is the basis for P2 and this one's the basis for P1. Okay. Okay. So what do we have to do? Well, first we need to build the matrix, right? So solution. We need to find. So remember, what did that theorem before say? We evaluate the linear transformation on these guys first, and then find them, find their coordinates with respect to these guys, right? So first, let's do that. So let's evaluate each one of them. So what's dx of 1? Well, that's 0, right? What's dx at x? Well, that's 1. What's dx at x squared? Well, that's 2x, right? Finding coordinates with respect to B prime. Well, what's the coordinate of 0 in the B prime basis? So what is the 0 in the B prime basis? So remember, all you have to do is do 0 equals C1 times 1 plus C2 times X. So what is C1 and C2? 0. Yeah, so 0, 0, right? What about 1 with respect to the basis B prime? What is C1, C2 in that case? So remember, it's 1 equals C1 times 1 plus C2 times X. Yeah, 1, 0, and then the coordinates of 2x with respect the B prime basis. So remember, it's 2x equals C1x plus C2x. 0, 2. So that means A is going to equal to 0, 0, 1, 0, and 0, 2. Okay. So now I told you that this matrix is going to take, it's going to, now if you actually apply this matrix to a polynomial, it's going to take the derivative. And how is it going to do it? Well, just I guess watch. Making perfect. Well, then, so if we have a polynomial of degree 2, so say ax squared plus bx plus c, right? I don't know. Let's make it concrete. Let's say it's x squared plus 3x plus 1, right? The coordinates of, what is the coordinates of this polynomial with respect to the basis b? Well, x squared plus 3x plus 1 with respect to b is just the vector 1, 3, 1, right? Now do this. So this is now do 0, 1, 0, 0, 0, 2 times 1, 3, 1. What is this going to give me? Well, it's going to give me a, so it's going to be 3 and then 2, right? Let's see, did I do the right order? 0, 1. Yeah, yeah. So, by the way, this represents the x squared component. This represents and yeah. Anyway, so this gives me that vector, right? Which means that if I plug in my, so if I plug it back into the formula, ax squared plus, ax plus b. This part right here is a, and this part here is 3. So plug it in, you get 2x plus 3. Isn't that the derivative of x squared plus 3x plus 1? I mean, right? Yeah. So you see how this matrix did exactly what the linear transformation was going to do. The linear transformation was defined as the derivative. We represented it as a matrix, took the polynomial in the new basis and applied it on it, and it took the derivative of it. So we're going to do more examples on it because I feel like maybe this was a little, I don't know, out there. But we'll definitely do them on the homework for sure, because the homework has them basically. Any questions on this so far? Okay, that's fine. We'll have questions for the session, I guess. I mean the homework session. So I'm gonna skip 6.4 for right now. Reason is because I want to get into eigenvalues and eigenvector stuff already. Maybe something that's a little bit more familiar for you guys, because that one you just take, literally all you do is just compute things. That one you don't have to think about this like crazy stuff anymore. So yeah, so we'll come back to 6.4 probably next Friday. But for right now, let's do 7.1. So chapter 7. Eigenvalues and vectors. Eigenvectors. All right. All right. So basically, we're going to start with this. We're going to start with what's called the eigenvalue problem. Oh, and by the way, if you guys are anticipating like things with, if you guys have seen the end game for Adventures, it doesn't has nothing to do with the eigenvalue, what they talked about there. Well, a little, but not too much. But basically, this is the problem. Let's say I had a matrix A, okay? Suppose I have the n by n matrix A, okay? The question now I pose is this: can you find every vector in Rn such that when I multiply A on it, it will scale it. It will only scale it. Scale the vector. Right, so I take the vector, I multiply A on it, and it scales it by some constant. If I give you this problem, well, then you'd be asking, okay, well, I mean, how am I going to do that? I have to check every infinite possibility in Rn, right? You can also phrase it as, in other words, find every V in Rn such that AV is equal to lambda V, or lambda is a scalar. Okay. So, okay, so the question is simple enough. So I want to find every vector such that A times V is a scalar multiple of V. Okay. Okay, well, how do I even like try to attempt to do this? Let me add one more restriction. Let's just say V is not 0, okay? Because if it's 0, then obviously everything is a scalar multiple of it, right? So let's just add the condition where we're not, the 0 vector doesn't count. Let's just find everything that's non-trivial. So the answer to this problem becomes this. So take this. AV is equal to lambda V, right? Subtract both sides by lambda V. AV minus lambda V is equal to the 0 vector now, right? Factor out of V, out from the right-hand side, you get AV minus lambda I. V is equal to 0. Now, from here, this should look very similar to us. So this looks similar to AX is equal to 0. Oh, well, I guess this is it. Like in general, right? Like we've studied this already, right? AX equals 0. Now, let me ask you, so everything that you've learned so far, what can you do? Oh, sorry, and there should be just A. what can you do here to guarantee that this v is not 0? What can you check in order to guarantee that this v is not 0? So think about remember how we talked about equivalent statements like this solution has a non-trivial vector, means A is invertible, means, so what can we use out of those, like, I guess, equivalent statements of what we learned in order to guarantee that v won't be 0? So remember, ax equals 0 does not have trivial solution if what happens? Or in other words, ax equals 0 only has a trivial solution if what? Think in terms of determinants. If the determinant is what, will give me this. If the determinant is not 0, then the only solution to this is x equals 0, right? So if the determinant is 0, it means that there is a non-trivial solution for this, right? So basically, if you take the determinant of this guy, which is just the matrix A, minus lambda I, and you set it equal to 0, that should give me all the lambda values that would guarantee me that the vector v is not 0. If you solve for this, you will get what's called the characteristic polynomial. Then you just do like a college algebra problem. You find your lambdas, and those are your eigenvalues. So we'll do examples of this next time. But this is how you solve the eigenvalue problem. You use things that you knew from determinants in order to guarantee that v is not 0. But yeah. So next time we'll talk about how to find the, we'll do an example of finding the eigenvalues, and then we'll look at how to find the eigenvectors. All right. We will continue this Monday. Yeah, all day May 7th. Yeah, but I might push it to the 7th as well. For sure. I'll just I might push it to the 7th, and I will. To anybody who wasn't here, like I said, I'm gonna do a homework session tomorrow at 9 a.m. and I'll so you get, and I'll have the problems worked out on my paper. Yeah, for sure. Here.
I didn't really understand if you wanted me to wait for another.
Oh, I can open it. I had opened it yesterday.
Oh, really?
Yeah, but I can open it again. Okay. Yeah. But tomorrow at 9. Yeah, some of them. Yeah, for sure. It is kind of some of your homework as well. But if you do all the homework, then I guess it wouldn't really matter. So, yeah.
Thank you.
No problem.